we looked at this Lagrange multipliers. We just had a very basic introduction, right? But there are a couple of good questions that I just wanted to briefly mention. Before we did that, we looked at maximizing and minimizing functions, surfaces, right? And there was a question about the sign of not the f sub xx, but the question was, could we just replace f sub xx with f sub yy? And I said, yes, there's many ways of there's alternative versions of this second derivative test, okay? But why does it work? That's a better question here. So you think about if the d is positive, right, at the critical point. Now, that bit's always going to be non-positive, right? So the only way for this mess to be positive is if these two things have the same sign. Let me say that again. The only way for this d to be positive, if it's positive, these things have got to have the same sign. They've either got to be both positive or both negative. So you can switch out f sub xx with f sub yy if you want to, right? But just be careful. The Mobius questions ask you about f sub xx, okay? So you can fight the power if you want to and go, no, you will not control me. I'm an individual. I will do f sub yy. You can do that. You can fight the power, but you may not get a mark for it on Mobius, okay? I'm just being honest with you here. All right. So in the last class, we looked at what's called the del operator. Okay, and this is our first step into proper vector calculus. Okay, so the del operator is this vector, and it basically takes a function like this phi here, and it outputs a vector with the partial derivatives as the components. Okay? And I made a claim that, say, if you're at a point P on the surface, right, so this is the surface phi equals 6, let's say, then the gradient vector at that point on the surface is normal to the surface. So it sticks out either that way or maybe that way. Okay? Okay, so I also showed you, can we have the feed to the document camera? Should be on there. Let me know if the feed's not coming through at home. It should be coming through. All right, so in preparation for should I sound terrible? Shut up. In preparation for this method we're going to call Lagrange multipliers, I posed a problem towards the end of the class yesterday, right? So find the point on the line that's closest to the origin, okay? And basically it's like blowing up a balloon, and you make the balloon big enough until it just touches the line, okay? And there are two vectors in that picture. One is normal to the line, and the other one is you've taken the del of x squared plus y squared equals whatever squared, okay? What did we notice about the two vectors? They're parallel. That's the most important thing, right? For these problems, the method of Lagrange multipliers, which we'll formally learn in a minute, that's the most important thing. at the points of interest of maximising and minimising, the normal vectors either point in opposite directions or in the same direction. They're a multiple of each other. Okay? So, let's do a problem and we'll sit down and work through it. Okay. All good now, great. All right, so let's look at this problem. So you've got a disk, and it sits in the xy plane, and you've got a function. So here's a function. Determine the highest and lowest temperatures on the edge of the plate. So basically on a circle. Yeah? So it's not a difficult problem, and you can do it a range of ways, right? But let me show you how you can do it using these vectors and whatnot. Okay. So here's a little sketch of the domain that we're interested in. X squared plus y squared equals 5 squared, because we're on the edge, right? And so we've got two pieces of information in this problem. So this is our f. And we've got a constraint. And this is sort of the standard setup. You have a function that you're interested in learning about, and you have some condition, which we usually write as g equals 0. Okay? Now, you could probably take this g equals 0 and sub it into f and then use regular calculus to find the maximum and the minimum. Maybe you can do that. That's not the point of today's ideas, okay? But sometimes you can do it. Sometimes these problems are super easy. But let's think about it for a second. Like I was saying yesterday, in these problems, the idea is to look at the normal vectors, okay? Look at the normal vectors. So, we're going to solve this equation. Okay, so what does that say? That says, if you apply the del operator to f, it's a multiple of the del operator of g. Okay? We have a special word for this. We don't say del of f or something. We talk about the gradient. So it's grad f equals lambda times grad g. Okay? So we say gradient or grad f, or, you know, you could say the del of f, but gradient's easier. Okay. So let's just unpack that for a minute, because now I'm going to make a connection to what we did yesterday, okay, about, remember, the critical points and the partial derivatives being 0, all that sort of stuff. We can use that, right? We can use that. This is the same, right, as the following problem. I'm going to introduce this L function called the Lagrangian, and I'm going to look at the critical points. Okay? The critical points of L. Okay, let's have a look. So f's a function of x and y is a function, g is a function of x and y. So we wouldn't worry about the third derivative up here. We would just do the first and the second, like ddx and ddy. Okay? Okay, so that's our first derivative that we're interested in, and we set them to 0 for the critical points. Okay, who can tell me, without doing any calculations, what is that system equivalent to I've already written down?
The del operator one? The del operator one?
Yeah. These equations and that equation are the same. They're the same equation. One's just compact, written compactly with squiggles and triangles. The other one's written out in a longer form. Okay? So if you're doing a problem like this, I don't care which way you solve it. You can solve it using that above, grad f equals lambda times grad g, that's fine. Or you can define the Lagrangian L, differentiate it and set it to 0. It's the same problem. Okay? So if you look at some of my YouTube videos, I don't even mention this. I just go straight to this. Whereas other videos, I don't mention that. I go straight to that. Okay? So it's up to you. You can choose. You can decide whatever works for you, whatever's easier. Okay? So I'll do it this way, and then on another one, maybe I'll do it the other way. All right, questions so far? I know it's still early.
Why do you set the Lagrangian to 0?
Which Lagrangian are you talking about? Well, the top. So see where it have solve grad f equals lambda grad g. That tells you the two normal vectors are parallel. And we discovered yesterday that generally that's the case when you want to maximize or minimize something with a constraint. The point of interest is where the two vectors, the two normal vectors, point in the same direction or in opposite directions. Yeah. Other questions? It's a good question, by the way. Okay, all right. So now it's like, okay, what we want to find, the point x and y where this happens. You can also find the scaling value of lambda if you want to, but it's not so important for the problem, but sometimes it's helpful. Okay, so let's do it for our problem and see what happens. Here's our f. So f sub x is going to be 8. Well, you can even simplify this even further, right? It's 2 minus 2x minus y all squared. Okay, so you can actually simplify that if you want to. Okay? So you can kind of see what's going to happen with the turning points of that anyway. All right, so if I differentiate that, I'm going to get, the 2 can come to the front, the 2 goes over there. You're going to get something like this. And then minus lambda times g sub x. So what's the derivative of this with respect to x? It's going to be 2x. Okay, let's go up here, differentiate with respect to y. The 2's coming to the front, the 1 comes to the front. Decrease that by 1. And g sub y, 2y. Okay, now you're at a stage where you need to do some calculations, but people freak out because they go, hang on, there's 3 things in there, Chris. There's x, y, and this, whatever this lambda is. But fear not. There's a third equation that is hiding. the constraint equation. Okay? The constraint equation. So we're going to use that maybe. Sometimes it's helpful to use it. All right, so let's call this equation 1, equation 2. So the way I've done it, I've just added 2 lots of equation 2 to equation 1. Brilliant. And I get something like this. All right, great. So now, although we've got 3 things, we can still simplify a little bit. So lambda 0 or x is negative 2y. So we get like a line. Okay, so we'll do something with that in a minute. Okay, I'm going to break that up into 2 parts. Let's just consider the case lambda equals 0. See what happens. Sorry, 2y, not 2 lambda. All right. So, if lambda equals 0, what does say equation 1 give you? It gives you y equals 2y, y equals 2x. And what happens then, you can get x from the constraint equation. A lot of people, when they're solving these problems, they get tied up because they think, oh, I've got something, it's not exactly what I want. They forget about the star constraint equation. Okay? Excellent. Okay, so we've got 2 values for x. For this case, let's go back and find the corresponding values for y. Okay, well, it's pretty easy. I can get it from there. So the sign's not going to change. All right, so our first points of interest. For this case, lambda equals 0. Are these 2 things. Okay, so we're halfway there. We just need to look at the case x equals negative 2y. And then we can make a conclusion, right? Okay, so again, the constraint equation can be helpful here. So, sorry, x equals negative 2y. All right, so we sub that in for x. We'll get this. Yep. And now, because we're going to change the sign on that, we'll get, say root 5, negative 2 root 5. Negative root 5, positive 2 root 5. Something like that. Yeah. All right, so our other pair of points of interest. Okay. So we've got 4 points of interest. A bit annoying. It'd be better if we had 1 or 2. Right? That would be ideal. So what can we do now? Can anyone suggest something? Let's go back to the original question, because we've got some data now. We've got some information. What are we trying? I'll put this back up in a minute. What are we trying to achieve? We're trying to determine the highest and the lowest temperatures on that disk, right, on the edge of the disk. So actually we're trying to maximise and minimise. So can anyone suggest what we might do now? If we've got the points of interest, what would we do? How would we find like the maximum and the minimum?
Second derivative?
Oh, good suggestion, but not necessarily. It might work, but even simpler than that. No calculus required. No calculus required.
Evaluate them in fxy.
That's what you're going to say too? Yeah, you're absolutely right. So we've got 4 points. Let's just work out the temperature at those 4 points, and then we'll compare them. The biggest one, that's the maximum. The smallest value, that's the minimum. Okay? So, go up here, evaluate f at points A, B, C, and D. Okay? So, when you put some of these in, you actually get the same values. The way I've calculated it, so you take, these values, put them into F, right? Okay, so if you do it, this is what I got. 2 of the temps are 0, and 2 of the temps are 125. Okay, so now you just compare them and you choose the biggest ones. Okay? Let me just put this up from home. Is it always the case that for the 2 different conditions, the values of x and y swap? No, it's not always. So, there's no hard and fast way to solve these Lagrangian problems, right? So you need to be a little bit strategic. You just need to try stuff. I'll do a range of stuff, but the more problems you do, the better you will get at solving them. Okay? Now, what haven't I calculated in this problem? I've got the x points and the corresponding y points, but what else? What else is in this problem that I actually haven't calculated? I've got the temperature, there's another variable in there that, what? The lambda, exactly. Do I care what lambda is? Not really. I don't care, right? But sometimes calculating lambda can help you solve the problem. Okay? There's only going to be one lambda, I think. But sometimes calculating that will help you solve the problem. Okay? So let me go back to my document camera for everyone at home. And I'll just catch up. Yeah. Okay, so you can see this problem, it's a little bit annoying because there's a few things to manage. But it's more long than it is difficult. Okay? It's more long than it is difficult. Questions? Yeah, you first. I'll come right to you.
I was just wondering, the question said that we had a disk as opposed to like a circle. Is there some way that we compensated for things in the inside of the circle rather than just the edge?
So, you want pass? So let me see if I can do this. So this is definitely a disk, right? So I can shade that in, yeah? I feel like I'm accepting a speech, an award, and I have to lean over. But the question says, what happens at the edge of the disk? So we actually don't care what happens on the interior, right? We don't care. If you did care, then you probably the Lagrange multipliers wouldn't work, right? Yeah, so don't get fooled by that. Make sure you read the question carefully. And I get it, right? Like a lot of students, they choose maths or engineering because they don't want to read anything, right? I get that. You know, I do feel bad for the Mobius quizzes where there's like an avalanche of words, you know? It's like, that's too much to read. Hopefully this is not too much to read. Does it answer your question? Yeah. So just be a little bit careful. Yes. Yes.
Why do you not consider the boundary points of the constraint function?
Say again.
Why do you not consider the boundary points of the constraint function?
Where? Okay, good question. Where are the boundary points? We're on the boundary.
What about the ones that intersect with the x and y axes?
So, well, if I have a circle, does it have a boundary? It's closed, a closed circle. It's no boundary. It folds up on itself. Like, you should be working. So if I have a line segment, like that, the boundaries are there, right? But if I put it, if I make a loop, there's no boundary. Is that what you're asking?
Kind of, yeah.
Have a think. Okay. Can you just pass the way?
I figured out the answer.
Oh, okay. What was your question? Okay. All right. Yeah. Of course.
Just another question. With the Lagrange equation, f minus lambda g, what is that derived from?
So, see that?
Yeah.
Yesterday, I should get one. Thank you. So yesterday, we were talking about how the normal vectors to these constraint problems are parallel. So this and this are identical equations, right? And I say, oh, let L be that, just so it's the same process as finding critical points. So you can connect it with something we've already learned. You don't have to do that. You can just work with the, grad f equals lambda grad g. You can do that. I won't be upset, right? But this is just a way of connecting it with something that you have seen.
When we see questions like this in Mobius tests or lab tests, would they always be 2 variable or could there be 3, 4 variable?
Oh, probably not 4. 4 would be a bit rude, I think, right? Although I have heard, back when we used to do handwritten exams, I had a colleague and he goes, yeah, I just set a Lagrange question. There were 8 points to consider, 8 sets of points, and they're all like square roots and everything. I think the best way, and I'll show you some examples today. I think the best way is just to look at, say, the class test practice questions and see what happens. I was a little bit surprised by the lab test, is it lab? Mobius quiz 1. Let me show you. I'll show you. Why don't I just show you? Hang on. Do I have... Because it's a good question. Okay. What? Try again. Oh. Okay. Okay, so here's one from this week. So what have we got? We've got a plane and we've got some sort of constraint that involves, I guess it's like the cross sections are going to be ellipses. It's like an ellipsoid. Right, I'll show you a picture in a minute. Right. Okay. Oh, that's a critical point question. Okay, this is probably as difficult as it gets. So your function that you're interested in, they've got a temperature function here. It's got 3 inputs, x, y, and z. And the surface involves 3. Okay? I don't think you get anything harder than that. Right? So let me have a look at last year's class tests. Okay. Hang on, not yet. All right. Here's an example. So, from the maximum value of this function, linear function, x plus 4y plus 4, and you've got another constraint. So the constraint is like the red surface, and the horizontal plane, or the plane, I guess, is the function you want to maximize. Okay? Now, just a top tip, the picture's there for a reason, I think. I don't set these questions, but I think the question there is for a reason, and it's to make your life easier, right? So just by looking at that picture, and I'm thinking about everyone at home as well, hopefully you can see the picture. What can you say about the maximum value of the plane on that ellipsoid? Is it on that red, like subject to the red surface? What can you say about its position? Look closely. Look closely at the picture. I know it's early.
You can see its values about 20, and one of the values, x or y, I don't know, is about 0.
Yeah. What about the other one?
It's about 3 or 4 or something.
Let me scroll down.
Yeah, there you go. X is about 0, y is about 4.
Yeah. So one of them's positive, right? The y value is positive. You see, at the other end, it looks like it's going to be negative, right? So down the other end, down here, down there, definitely the y value is negative there, right? And up here, the y value is positive. So that already helps you rule out some cases. You can say, just from the picture, I know that this thing, who cares if the y is negative? It doesn't actually play into what I want. Okay? Okay. So that, going back to your question, 2 equations, 2 unknowns, or 2 things really. Let's see if there's anything else. Okay, so that looks very, very much like the question from this week's Mobius quiz, the one that I just showed you. Okay? So that, I reckon that's probably the most time consuming. Okay. All right, let's do any questions from home. Okay, not yet. All right. Now, some of these questions are super simple. Okay, now I'll do one of those in a second, but let's just go through the bigger picture here. If you haven't worked it out, the way I think most people learn, and the way I like to teach, is I start with case studies, and then we say something more general after we've learned something about a special case. Okay, now that's dangerous because sometimes, you know, a special case is true, but the general idea isn't true, right? But I try to pay attention to that. I don't usually go the other way. I don't go from the big theorems to the examples. That could work too. I just think that's how most people learn. They start off with something concrete and they expand it. Okay, so suppose you've got a function, f, and you want to maximize or minimize it, and you've got some constraint. You can calculate the critical points of this, which is equivalent to solving that problem. Now, you don't need to know lambda. Lambda is nice if you can get it, but you're more interested in the points, the x, y, and z points. Okay? Now, it's easy to say, but some creativity is required. You know, and it's hilarious when you hear teachers say this, right? It's like, just be creative, right? Someone messaged me once, like I did say this in a lecture, right? I said, just be creative. Someone said, I cannot be creative. Right? What do you say to that? Like, yes, you can. I believe in you, right? Like, I didn't know what to say to that. If you find more than 1 point, compare the values. The biggest ones will give you the maxima. The smallest values will give you the minima. Another good question here is, how do you know what you're working with is a maximum or a minimum? Usually it's told in the question. Okay, so you don't need to worry about second derivative tests or anything like that. Okay, it's usually told to you. And in the third dot point, you're comparing anyway, so you can say, oh, that's bigger than that, that's smaller than that. Okay, now, sometimes we want to work smarter, not harder. Okay? Now, you could do this using Lagrange multipliers. But is there a better way? Is there a better way early on a Wednesday morning?
You just solve like values, like I don't know how to say it. You can just see it.
You can guess it.
Yeah.
Maybe some guessing. Guessing and checking's not bad. I do it. But can anyone see how this is actually maybe a high school problem, and it's not actually like a Lagrange multiplier problem?
You just factor it?
Well, I think you can probably take the y in the second equation and put it into the first. Is that what you're talking about? So you'd factor it. That could work. So let's think about it. You could take that y equals x 16 minus x and put it in there and just use regular calculus. You could do that, right? But even easier than that. Let me draw a picture.
X and Y need to add to 16, and if you've seen a times tables chart, where numbers when they're squared are the biggest if they have to add up to a certain number.
Perfect. Algebraic, but we're on the right page, right? We're on the same page. Let's draw a picture, because then, okay, x times y. It's just the area of a rectangle. That's assuming it's positive, right? Okay, and what will the boundary B, right? What's the perimeter? 2x plus y. So it's one of those problems that many of you would see at school. You've got to basically design a box or a rectangle with a limited amount of material for the sides. Okay? Are we getting flashbacks here? Yeah? Okay? And exactly what you said. How do you maximize the area? Well, when x and y are equal, it's the square. Right? So that gives you the maximal area. So okay, so x and y got to be equal, and their sum has to be 16. So, of course, x is going to be 8. That's it. So when you see these problems, like we're all human, right? And so we get conditioned into working in certain ways. I've done it, right? You get a problem and you just learn a method. Let's apply the method. But sometimes we just need to slow down and go, oh, isn't there an easier way? Right? People, you've seen this before. Some of you, I think most people have seen it before, right? Yeah. Okay. So you could set it up as a Lagrangian. Don't need to. If you get this in the lab test, happy days. Right? Questions? Now another thing would be take y equals 16 minus x, sub it in there, and then do your calculus. Okay. How's everyone going at home? How's everyone going at home? You still awake? Let me know in the chat. Okay, here's another one. So, one thing I don't know, why is the camera pointed at you guys? There's some, I don't know if you can, I've tried controlling it. Let me see if I can do something else. I don't mind that. I don't mind looking at you. That's fine. Let's try board. No? Oh, did something happen? Okay. All right, that'll do. Good, because you're lecturing. Okay, good. Absolutely sensational. Brilliant. Thank you. Okay, here's another one. Similar to the previous one, but just difficult enough to be annoying, really. Okay, another temperature problem. Use the method of Lagrange multipliers to solve it. Okay, so here's one I've created earlier. I'll zoom in a bit. Okay, first thing, identify your constraint function or your condition function, or your condition basically. Okay. So here, I've introduced the Lagrangian. I haven't worried about del operators or gradients or anything like that. I've just done it using the methods we learnt yesterday. Okay, so form the Lagrangian, in this case t minus lambda g, and find the critical points. That is the same as solving grad t equals lambda grad g. Okay, You get a bunch of equations and you can solve. Again, some creativity is needed sometimes. Okay. So if I use my constraint equation, I'm going to get a few different points. And then it's a matter of taking those points and calculating the temperature at each of them, and then comparing them. Okay. I'm just running out of time, so I'm just going to leave this up for a little while. All right, so 4 points to check. You come back. There. Hopefully I've squished it all in. Okay, you can see in my bad handwriting, there's actually 2 points. You've got some symmetry going on. That's sort of what explains it. Okay, so in this case, there's 2 places where the temperature is a maximum, and there's 2 places where there's a minimum. Again, symmetry. But you can see the method is the same, right? You just need to be able to solve the simultaneous equations that you get. And sometimes it's easy, sometimes it's like, oh, there's a false start, or you miss out a value or something. Okay? So the only thing missing from this would be a conclusion, but for your class test, you're just entering the values, basically. All right, let's take a break. And come down if you have any questions. All right. Now, this is again, just for repetition and whatnot, I've just listed the method up here in the bigger picture for these Lagrangian problems. But there's something wrong with this. There's something wrong. I was looking at this last night, and there is definitely something wrong with this question. Have a look at it. What's wrong with this question? Is there anything wrong with it?
Where you go?
Oh, is it like g of x, y, z as opposed to just g of x, y?
Yeah. That's one problem. Right? So what are we trying to do in this problem? We've got a plane and we've got the square of the distance function. Right? That's the f.
I thought the constraint should be like a circle.
Yeah, well, it will be a sphere. A sphere, yep. Say again.
For it to be a sphere, wouldn't that be x squared, y squared, z squared?
When you add them, you get a sphere. Yeah, and so no, that bit's okay.
Is the question actually asking what the closest point of the plane to the origin is?
Yeah. So that's exactly what it's asking, right? So how could it be a maximum? How could it be a maximum? How can you have a maximum distance from a plane to an origin? That doesn't make sense at all. Is there a maximum distance? If you have an infinite plane, and you want to find the maximum distance to the origin. Is that even doable? Yeah, it'd be infinite. Right? So the maximum actually doesn't exist. Okay? So not one person has corrected me on YouTube about this, by the way, in 12 years. So I can see people are looking at this really carefully. I think it should be the minimum value. Okay? It should be the minimum value. Because the other way it doesn't make sense. How do you have a maximum distance between a point and an infinite plane? No one knows. Okay? All right, exactly, maximum. Okay, so I'll do some problems in a second. So just give me a sec. Oh. Yeah, before we get on to the two constraints, should we do a couple of problems from the lab test? Okay, just take it easy. The reason I'm showing you this is that the problems can get harder depending on the number of constraints, the number of conditions. Okay, so in this case, I won't solve this right now. You've got something you want to maximize, and you've got two conditions. So it gets a bit crazy now, right? It gets a bit crazy. So how many parameters or lambdas you're going to have? You're going to have two. Okay? It's a bit hard to set up a picture for this, but you get the idea. Now you might be able to take one of these and put it into the other one and simplify. Great. But that's not always possible. But let me do an example from one of the class tests. So just give me a minute. Aha. All right, this is classic Lab Test 1 material, and you will get access to this at some point. Well, here it is. Suppose you've got a point on a plane, you want to compute the point that is closest to 2, 1, 2, 2, 1. Okay? Enter the exact value. So if there's square roots or something, you want to put in the square root sign. Okay? All right. So let's come back to the two constraints thing in a minute. Let's see if we can solve this one. So imagine we're blowing up a balloon, a balloon is fine, but the balloon is centered at 2, 2, 1. Okay, it's no longer at the origin, it's been moved. Okay, we blow it up until we hit the plane. Okay? That geometrically, that's one way of looking at it. All right, so we want to minimize we want to minimize that function subject to the points being on the plane. Okay? And let's use Lagrange multipliers to do this. There are other ways of doing it. Believe it or not, you can solve this problem using Math 1131. Algebra. Okay? If anyone knows how to do that, show me, because, you know, or try to explain it to me, because that would, you know, that helps. All right, so instead of computing the critical points, I'm going to use the gradient equation, okay? Just to mix it up a bit. Just to mix it up a bit. Okay? I can't be bothered writing down all those derivatives and everything. Okay? So this is one way to do it quickly. Well, I guess a little quicker. All right. The gradient of f. Okay, so gradient of f involves partials. Differentiate with respect to x and write it down as the first entry. Differentiate with respect to y and write it down as the second entry. Differentiate with respect to z and write it down as the third entry. Okay? Now do the same with g. So g is pretty easy. 3, 1, negative 1. Okay? So I've got three equations there. X, Y, and Z, I'm not sure about. Lambda, maybe I can get it. Oh, did I make a mistake? Oh, yeah. Hang on. Okay, so hang on. That's. Yeah.
Where did the f function come from?
Okay. So f is related to the distance. It's a square of the distance, right? So if we were minimizing distance to the origin, a suitable function would be x squared plus y squared plus z squared. Right? So you've basically got a balloon and you're blowing it up. Right? Technically, it's not the length, it's the square of the distance. It's just easier to do. So get rid of the square root sign, minimize the square when you minimize the distance function when you minimize the square of the distance. That's basically the idea. Does that make more sense? Okay. So you can see in each of these things we've got x in terms of lambda, y in terms of lambda, z in terms of lambda. So if I rearrange that, so that's the first line. Second line I can rearrange for y. Same with the third line. Okay? Now, I could go through and eliminate lambda, no worries, but I haven't used my constraint function yet with this problem, right? So what I'm going to do, I'm going to sub these three expressions into my constraint. Okay? I'll get something for lambda. Okay, solve that. I got lambda equals negative 6 on 11. Now, in previous questions, we haven't worried about the lambda too much, But why is lambda sort of nice here? Well, if you know lambda, you know x, you know y, and you know z. So it's a nice little byproduct of getting the lambda. Okay, so what does the question ask us for? It asks us for, let's just go back for everybody at home. The question asks us for the exact value of the x component of our point of interest. So we don't care about y and z, they don't actually ask us for it, right? So really, the only interesting thing, the only important thing there is one equation. It's this one. Okay? Okay, so I can put that into Mobius. Mobius acts a bit like a calculator. So I don't need to simplify, don't need to simplify. Shall we test it? Hopefully I'm all right. Oh. Okay. Now let's do the preview. So preview should simplify it. Yeah? So I really like it. I really like this idea of Mobius simplifying things for you, right? Because it hopefully means you make less mistakes or fewer mistakes. Questions? Yes. Sorry, I'm slowing down now.
Bit of a dumb question, I guess. How'd you get f, x, y, z? For, like,
Oh, yeah. So this was the same question as before. Okay, so let's talk about that, right? Because I'm assuming it's obvious and maybe it's not obvious, right? So where does this original equation come from? Okay, so I'll go back to the document camera for everyone at home. Where does the original equation come from? Okay, it's not the distance between x, y, z and 2 to negative 1, 2 to 1. It's the square of the distance. Okay, it's the square of the distance. Just imagine, so if you can't understand that, imagine a balloon at the point 2, 2, 1. It's got the center at that point, and you're blowing up the balloon. Yeah, well, sphere. Yeah. Okay. So if you set f to any constant, any positive constant, that'll be a sphere with a certain radius. Yeah. I mean, you could, instead of that f, you could have a square root over everything. That would be the true distance. But nobody wants to have square roots if you don't have to, right? So when we minimize the square of something, we're minimizing the something. That's the idea. Okay? Now, if you don't want to do that, and you want to have a square root here, be my guest. Good luck with those derivatives. Have fun with that. You can do it. It'll just take a bit longer. Okay? But it's up to you. You do what you want. Does that help? Does that help at all? So think of it as the square of the distance or a balloon. Balloon. Balloon's easier. Everybody loves balloons, right? Or a ball. Right? Other questions? Oh. What do we got?
Per se, but can we do one of the other normal ones that we did with critical points? Can we do one of them using this method?
Ah, yeah. So the question is, why can't you just find the critical points of f and use those? That's your question. It's not a bad question, it's a good question. Why can't I just use the critical points of f? Seems like a reasonable thing. Why can't I do it? Okay, you've got a sphere. Where are the critical points on a sphere going to be? So the tangent plane's horizontal, right? I guess there's a couple of things, right? You're going to have either the top or the bottom of the sphere, but that might not lie on the plane that you're dealing with. Remember, you've got the constraint equation, the plane. All the points have to be on that plane. So the top of the sphere and the bottom of the sphere, or wherever you have critical points, they may not be on the plane. That's why you can't use it. Right? Maybe it works out, but most of the time it won't work out. All right. Okay. Have a look online, see what's happening. Okay, be quiet online still. Okay. Let me just get my notes together here, just for a second. Aha. All right, here we go. This is as hard as it'll get for Lagrange multipliers. And it's extremely unlikely that you'll get this in a lab test. Extremely unlikely. Okay? In the final, I don't know. We haven't written the final exam yet. Okay, but you know, sometimes these kind of two constraint problems take a long time and you just tie yourself in knots. Okay? It's a nightmare. So let's have a look. Here's the function you want to maximize. But now you've got two equations. So they're both going to be planes. Okay, remember back to first year, Math 1131? How can two planes intersect? They intersect along a line, or they're the same plane. Okay, so there's a line of intersection, or they intersect everywhere. Okay? So how do you do it? All right, same sort of thing as before. I'm going to introduce the Lagrangian. But my Lagrangian's a little bit different this time. Here, I've got two constraints and two lambdas. Okay? So using this more general format, let's see what happens. Okay? So I'm not going to do grads or deltas or dells or whatever. Let's just do the Lagrangian and find the critical points of the Lagrangian. Okay? That should be enough. Okay. So differentiate. So differentiate that, and then put it into here, right? So it's going to, I'll just write it down. Okay, so this is what we're looking at. Okay, so let's do the derivatives. It's a little bit time consuming, but let's do it. All right, dx. So that'll become 2y. That'll become negative 2 lambda, lambda 1, and that's just 0. So critical points. Let's do derivative with respect to y. That'll become 2, that'll become lambda 1, and that'll become negative lambda 2. Okay, last one with respect to z, negative 2z minus lambda 2. Okay, so now we want to try to simplify that. We've got two constraint equations, remember. Okay, so there's probably a wide range of ways that you can solve this, but, you know, here's one way of doing it. Okay, if I simplify the first equation, x equals lambda 1, then I use this, I can see that I can get lambda 1 in terms of y. Okay? And have a look down here, I can get z in terms of lambda 2. Right, and then g2 equals 0, we can basically do the same thing as we did before. So here we're going to get, yeah. Okay, so we've got x in terms of lambda 1, y in terms of lambda 1, z in terms of lambda 1. Okay, so I don't know, let's get lambda 2. So let's call this 1, 2, 3. So lambda 2 is 2 plus lambda 1, right? Ah, yes. So, yes, thank you. Yes, thank you. Who said that? Thank you. Okay, so if we bring this together. So, solving, what do we get? Okay, so check these. This is what I got. And so now we have those, we can just go back and get our x, y, and z point. Great. Yeah. Okay, so x equals lambda 1, y equals 2 lambda 1, z equals that. Okay, so what is the question asking us to do? Maximize the function. That's the point that'll maximize the function, and so at A, you can work it out, right? Okay, I think that's what I got. So if you can cope with the algebra, that's obviously an important thing. But the method is the same. The only thing you've got now is two constraints. Like I said before, unlikely to be in a lab test. Concerning the final, it's probably unlikely to be in the final, but there might be some conceptual thing there. I don't know, we haven't written the final yet. Okay? All right, just give me a minute. Aha. Mm-hmm. All right, questions? Ooh. I think the Zs. Yeah. So from these, so sorry, I didn't explain that very well, did I? Right? So where does this come from? It comes from that and that. Those two equations. Sorry, I should have pointed that out. That's a good question. This is why you ask questions. It's great. So this and this give you that. Okay? But technically, you don't need the lambdas, right? What you're interested in are the x, y's, and z's. But sometimes the lambdas are helpful. Okay. Questions online. Oh, that was a good question. Somebody asked that online as well. Okay, let's do a lab test question for this, but only one lambda. Let me see if I can find it. Aha. Have I done it? Yes. Okay.